In these modules, we developed discrete-time Fourier transform, and this completes a set of Fourier tools for all types of signals. So for discrete-time aperiodic signals, we have this discrete-time Fourier transform, and then for discrete-time periodic signals, we can extend the discrete-time Fourier transform to cover both periodic and aperiodic types of discrete-time signals. The approach इसकी development में that we took is similar जो हमने continuous time Fourier transform के लिए किया था. We start from a discrete time aperiodic sequence and we consider a time limited sequence, that is, it is non-zero between minus n1 and capital N2, and then we create a periodic sequence by repeating this portion of the given signal and putting at n minus n and so on. And when in the limit we increase the period and when n approaches infinity, then x tilde n, which is the periodic sequence, it is exactly the same as xn. And then we observe what happens to the discrete time Fourier series equations in this limit. So the steps are the same. Discrete time Fourier series equations, and then we write the analysis equation AK. The important thing here is that summation is over n consecutive integers. So once we write these equations for x tilde n, and then in the analysis equation we can replace, because here we are summing over n consecutive periods, so we take this portion from here to here and we can replace x tilde n this equation with xn, and since then xn is 0 outside this interval, so the limits of this summation, they go from minus infinity to infinity. And then we introduce a transform function which is a continuous function in variable omega, and we notice कि ये जो coefficients AKs हैं, these are in fact the samples of this transform function at omega equal k omega naught. So this approach is similar, and because of the periodicity and frequency wrapping effect of E minus j omega n, discrete time complex exponentials, this transform that we introduce, it is periodic in variable omega, and its time and its period is 2 pi. And here we quickly derived कि ये वाकई periodic है and its period is 2 pi. Okay, then we plug the AK, which is now in terms of this transform function, back into the synthesis equation, and then we replace here 1 over n with omega naught over 2 pi. And I missed this omega naught in the video, but in the lecture notes I made this correction. And when the time period of this x tilde n, it approaches infinity, the periodic sequence becomes xn for all the finite values of n. And on the right hand side, when n is approaching infinity, omega naught, it approaches 0, so we pass from summation to integral. But here the interval of integration, it remains 2 pi, because we sum in this summation, we sum over n consecutive values. So the spacing, it reduces, but the total interval on which we integrate, it is 2 pi, and we get the discrete time Fourier transform synthesis and analysis equations. So Tuba, was this development clear to you? या अभी कोई questions हैं quickly?
सर मेरे ना इसके कॉन्सेप्ट इतने अच्छे नहीं हैं, तो शायद सही समझ नहीं आया था सर.
समझ नहीं है. So can you connect this development with the continuous time Fourier transform development?
यस सर, बट मुझे इस वाली की समझ नहीं आई थी। उसमें तो ये था ना कि हमने जो टाइम पीरियड था वो बहुत मतलब ज़्यादा कर दिया था कि वो अपीरियोडिक बन गया था। हमने
हाँ,
इसमें भी यही किया है ना?
इसमें भी हम बिल्कुल यही कर रहे हैं। So if you look at this, yeah, if you look at this x tilde and यहाँ पे अगर टाइम पीरियड हम इंक्रीज करते जाएंगे, सो ये जो कॉपी है इस सिग्नल की, इट विल बी पुश्ड फर्दर टू द राइट। तो बिल्कुल वही काम होगा जब n इंफिनिटी पे चला जाएगा, टाइम पीरियड इंफिनिटी पे चला जाएगा, देन x tilde n विल बी इक्वल टू xn। तो हम वही चीज कर रहे हैं जो हमने कॉन्टिन्यूस टाइम फोरियर ट्रांसफॉर्म की डेवलपमेंट में देखा था। बट या सो देयर आर सम डिफरेंसेस। वो ये है कि ये जो ट्रांसफॉर्म है x j ओमेगा e j ओमेगा, इट इज पीरियोडिक, ठीक है। और जो
यस
सिंथेसिस
सर।
इक्वेशन है, लिमिट्स ऑफ इंटीग्रेशन, उसका जो इंटरवल है दैट इज इक्वल टू 2 पाई। और टाइम डोमेन में नाउ वी हैव अ डिस्क्रीट टाइम फंक्शन, और ट्रांसफॉर्म डोमेन में वी हैव अ कंटीन्यूअस फंक्शन इन वेरिएबल ओमेगा। Okay, and the fourth point is there is duality between discrete time Fourier transform and continuous time Fourier series. अगर हम याद करें, now everything is sort of connected. Continuous time Fourier series में क्या था? We were representing a continuous time periodic signal as a linear combination of complex exponentials. तो यहाँ पे जो transform function है capital X e j omega, it is a linear combination of complex exponentials, लेकिन इसके weights क्या हैं? xn's हैं, which are provided by this aperiodic sequence. और the sign here of these complex exponentials, it is minus. और वहाँ पे जो हम analysis equation use करते थे a case find करने के लिए continuous time Fourier series में, over there we were integrating over one time period of the periodic signal. So discrete time Fourier transform is dual, and there is cross duality with the continuous time Fourier series. Iman, do you have any questions here?
No, sir, it was clear. Thank you.
Good. So the next module we did some examples, or in
सर
yes,
सर मुझे सिमिलैरिटीज और डिफरेंसेस की समझ नहीं आई थी सही से।
differences की समझ नहीं, कौन सी difference की?
सर लास्ट में यस सर यहाँ पे
duality वाला?
यस सर, और सिमिलैरिटीज।
Similarities तो वही हैं, because we are now representing aperiodic signal as linear combination of complex exponentials, ठीक है। और capital X e j omega, it is the spectrum, because it tells us के कौन सी frequencies हैं, and it is a continuum of frequencies which are present in this aperiodic sequence. और यहाँ पे this third point on the similarities, discrete time Fourier series coefficients, ये क्या है? We can think of them as the equally spaced and scaled samples of this transform function because of this development. ये discrete time Fourier series के coefficients हैं. So once again I will connect with the continuous time Fourier transform case. वहाँ पे क्या था? वहाँ पे भी जब हमने aperiodic continuous time signal का Fourier transform लिख लिया था, and from the construction, and we did examples as well, square wave वाली example हमने वहाँ पे देखी थी। तो अगर हम उससे periodic signal दोबारा बनाते थे, periodic signal के जो Fourier series coefficients थे, they were the scaled samples of the transform function, and same thing is here. तो अगर हमें discrete time Fourier transform किसी function का पता हो, किसी सीक्वेंस का पता हो और उससे हम एक पीरियोडिक सीक्वेंस बना लें, then using that transform we can find the discrete time Fourier series coefficients of the periodic sequence. ठीक है, so it comes from here. A केस ये discrete time periodic sequence के coefficients हैं, okay? और जब हमने ये transform function introduce किया which we later called discrete time Fourier transform, तो अगर हम इस function में ओमेगा को k ओमेगा नॉट सब्स्टिट्यूट कर दें, we will get, और फिर 1/n से मल्टीप्लाई भी कर दें, we will get these a केस. ठीक है तूबा?
Yes, sir.
और डिफरेंसेस में डुअलिटी में you have a problem?
Yes, sir.
Okay, so quickly अगर मैं यहाँ पे continuous time Fourier series की इक्वेशंस लिख दूँ, xt if it is a continuous time periodic function, तो हमने इसको कैसे रिप्रेजेंट किया था, k इक्वल माइनस इंफिनिटी टू इंफिनिटी a k e j k ओमेगा नॉट t, और a केस continuous time के केस में. Okay, now I am writing these equations for continuous time Fourier series for continuous time periodic signals. So we had 1 over t integral over 1 complete period xt e minus jk omega naught t dt. And now compare these two equations with discrete time Fourier transform equations. ये जो analysis equation है, its form is similar to the synthesis equation here, isn't it?
Yes, sir. Yes, sir.
Okay, form similar है because यहाँ पे we are expressing xt as a sum of these weighted complex exponentials, and xt is a periodic signal. तो यहाँ पे capital X e j omega, this function, this looks very similar to this one. और ये जो AK है, this form, its form is very similar to this discrete and Fourier transform synthesis equation, isn't it?
Yes, sir.
The role of omega and t is reversed, और जो sign है exponentials का वो minus हो गया. That's it. This is the only difference. So that's why we can say that there is cross duality between discrete time Fourier transform and continuous time Fourier series. Okay.
Yes, sir.
चलें. So on to the next module now. यहाँ पे we did some examples, और पहली जो example हमने की थी that is a right-sided exponential decay, and for convergence we need the absolute value of a to be less than 1. So there are two possibilities. If you recall, जब हमने discrete time exponential signals पढ़े थे, if the value of a is positive, तो इस तरह का decay हमें नजर आएगा, और if the value of a is negative between -1 and 0, then there will be sign reversals there. तो इसका discrete time Fourier transform find करने के लिए all we need to do is to use the transform formula here, or okay, and then evaluate this summation. और यहाँ पे when we come here at this step, because of this condition, this magnitude is less than 1, so we can use a infinite sum formula and we get this discrete time Fourier transform. Okay, और फिर यहाँ से हमने इसका magnitude और phase find कर लिया. Any questions कि हमने ये कैसे derivation की थी?
Sir? Hello?
Hello, who is this?
Hello. अस्सलाम वालेकुम सर.
वालेकुम सलाम.
सर मुझे एक बात समझ नहीं आई थी कि आपने मैग्नीट्यूड कैसे इसका लिख दिया?
Okay, so हाँ, मैग्नीट्यूड हम कैसे फाइंड करते हैं? कैन समवन हेल्प? I don't know who asked this question, but can someone answer this question?
सर मैं ही बताता हूँ। हम इस तरह लेते हैं कि जो हमारे पास न्यूमरेटर होता है उसका मैग्नीट्यूड फाइंड कर लेते हैं और डिनोमिनेटर का फाइंड कर लेते हैं मैग्नीट्यूड।
Okay.
जो इमेजिनरी पार्ट होता है उसका स्क्वायर और रियल पार्ट होता है उसका स्क्वायर कर लेते हैं और अंडर रूट ले लेते हैं।
ठीक है।
हाँ, तो सर इसमें डिनोमिनेटर कैसे लिखा है मुझे समझ में नहीं आई।
तो डिनोमिनेटर यहाँ पे हमारा है 1 माइनस ए ई माइनस जे ओमेगा। ठीक है, तो यहाँ पे अगर हम आइलर लगा दें, दिस इज वन वे ऑफ डूइंग इट, तो वी विल गेट 1 माइनस ए कॉस ओमेगा प्लस जे ए साइन ओमेगा, इजंट इट?
जी सर जी।
ठीक है, तो अब हमारे पास नाउ वी कैन टेक द स्क्वायर ऑफ द रियल पार्ट एंड द इमेजिनरी पार्ट एंड देन टेक द अंडर रूट।
ठीक है सर।
ठीक है,
ठीक, थैंक यू।
अच्छा, so this है okay. So then we plotted the magnitude and the phase functions. So यहाँ पे the interesting thing that you should notice कि case 1 में when A is positive, the magnitude plot looks slightly different than when A is negative. And जब A positive है तो जो lower frequencies हैं, because in discrete time pi is the maximum frequency, so हमने फिल्टर्स पढ़ लिए हुए हैं। अगर ये किसी LTI सिस्टम का इम्पल्स रिस्पॉन्स होता तो इफ A इज पॉजिटिव, इसको हम क्या कहते हैं, हाई पास या लो पास? So my question is, if this xt, if we have an LTI system जिसका इम्पल्स रिस्पॉन्स ये सॉरी xn हो, ये सीक्वेंस हो और उसका ट्रांसफॉर्म ये है, एंड इफ वी चूज A between 0 and 1, तो उसका मैग्नीट्यूड हमें ऐसा नजर आता है, so it will be low pass or high pass. How do we classify the system? Can anyone answer it? So this will be low pass, and when A is negative, this will be high pass, because now at pi the magnitude is high. So this filter will be more selective for the high frequencies. It will pass high frequencies and it will pass low frequencies. So this will attenuate high frequencies, this will attenuate low frequencies. Yes, Abdullah, you are right. This case 1 is low pass, case 2 is high pass. Okay. And now on to the next example, rectangular pulse. Okay, now here we have this rectangular pulse और हम इसका discrete time Fourier transform find कर रहे हैं यहाँ पे. So the discrete time Fourier transform, you must have seen this this example जब हमने periodic case में. Have you studied filtering in detail? No, Jamshed, we have not studied filtering in detail, लेकिन हमने जो properties discuss की थी continuous time Fourier transform की, और फिर इस module में, so we have not formally studied filtering, but as explained in these modules, LTI systems basically they act as filters. तो उस सेंस में yes, we have seen some filtering, लेकिन हमने formally नहीं देखा कि filters कैसे डिजाइन करते हैं. So you just have some rough or basic ideas about filtering. Achha. So here, when we use finite sum formula, so we get this expression, and then we go from here to here, which is sine omega n1 plus half divided by sine omega over 2. And this is a periodic sinc function. Okay, we call it a sinc function. The form is different, but it's not what we defined as a sinc. It is a periodic sinc function, which becomes clear from the plot. And because this discrete time Fourier transform is periodic, we can very clearly see that this has periodicity. और हम इसकी zero crossings और maximum value we can very easily find. Maximum value at omega equal to 0, we find it using L'Hopital rule, and then zero crossings, जहाँ पे numerator is a multiple of pi. So any questions about this example?
सर आपने यहाँ पे जीरो क्रॉसिंग कैसे कैलकुलेट की थी?
जीरो क्रॉसिंग मैंने ऐसे कैलकुलेट की कि अगर हम इस न्यूमरेटर को देखें तो we have omega n1 plus half, okay, and from here sin कब zero होता है when its argument is a multiple of pi. So omega n1 plus half, whenever this is a multiple of pi, तो numerator zero हो जाएगा, ठीक है? And from here we can get the zero crossings का जो formula है, if so this becomes 2 pi m divided by 2n1 plus 1. ठीक है? Does it answer your question?
Yes sir, yes sir. Thank you.
Okay. Okay, so keep in mind, ये जो sinc है, this is periodic sinc. Okay. Any other questions before I hand over to Momin? Momin, I think I am done with the 2 modules.
Oops. So नवीन मैंने आपको ये प्राइवेट में भेजी थी.
I made you host, Momin.
Okay. 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 Achari. So the next module is, let me start my video. Yeah. So next module is discrete time Fourier transform of periodic signals. Or I mean, the treatment here is going to be very, very similar to what we did in the continuous time case. So we're going to start with the most basic of complex periodic signals that we can think of. और वो क्या होते हैं? वो एक complex exponential होता है, right? So let me see, मैं record कर रहा हूँ. Yeah. Okay. So how do we go about this? I need to determine the Fourier transform of this signal. One of the ways I could do it is, I mean, I just apply the forward Fourier transform relationship and try to determine what this sum is. It turns out this does not converge. Okay. अब ये convergence के issues हैं इसके अंदर. Even though I would urge you to try to think about कि जी अगर मैंने इसको solve करना होता तो क्या करता? So you would have to work in the limits. यहाँ पे n equals minus capital N to plus capital M करें, you see what it looks like, and then take the limit. You'll actually find that it indeed turns out to be this train of impulses. But that's a little bit more advanced. The way we go about this is that we do some sort of reverse engineering, and then we say, let me just consider a test case. Okay, this is a train of impulses in the frequency domain, right, which resides in omega naught and then periodically extends itself all the way up to infinity with a period of 2 pi. And let me just try to find the inverse Fourier transform of this and see for what it looks like. And lo and behold, when I apply the inverse Fourier transform relationship, blah, blah, dot, 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 karte, karte, x of n turns out to be that complex exponential that I started out with. So the conclusion, which is an important conclusion, is this equation number 1, right? So the Fourier transform of a complex exponential in discrete time is 2 pi times the summation of train of impulses. So e raised by j omega naught n ka Fourier transform kya hai? This is a train of impulses. The first impulse at residing in omega naught, the second one in omega naught plus 2 pi, omega naught plus 4 pi plus 6 pi, इसी तरह all the way up to from minus infinity to plus infinity. ठीक है? Okay, Jamshed has asked, why are we using integration for Dtft? Why should we not use integration for Dtft, Jamshed? फिर क्या यूज करें? शायद अनम्यूट करें अपने आप को. Why summations? See, here's so continuous. So that's what we started at the beginning. Okay, discrete time Fourier transform. What does it mean? You have a signal in the time domain which is discrete time. Okay, so if you want to go from this time domain to the frequency domain में जाते you would have to take a summation. That's for sure. That's for sure. This is what we've done here. I am going from the time domain to the Fourier domain or the frequency domain. I would have to use summations because the time domain signal is discrete. However, the Fourier domain is continuous. Right? The Fourier domain is continuous. This omega is a continuous variable. Right? It's a continuous time variable from minus infinity to plus infinity. If I want to go back from omega to x of n, I cannot have a summation here. Why would I have a summation here? Right? So because omega is continuous, I have to have an integral. One of the other ways you can think about this is x of n, even though it's discrete time, it's made up of complex exponentials over a continuum of frequencies. Okay, that's important. So even though x of n is discrete time, that discrete time signal is actually made up of discrete time complex exponentials, which have frequencies over a continuum of an interval of 0 to 2 pi. Okay? Okay, Jamshed? All right. So let me move on. ये बाकी लोगों को समझ आ गई? So this is very important. I mean, continuous time Fourier transform में we had a time domain signal which was continuous, and then we went to the Fourier domain, and the Fourier domain was of course continuous, and the frequencies were from minus infinity to plus infinity, right? We had a continuum of frequencies which made up that continuous time signals from minus infinity to plus infinity. Discrete time may be more or less ऐसा ही है कि the discrete time signal is made up of a superposition of discrete time complex exponentials. However, the frequencies of those discrete time complex exponentials has to take on values over a continuum, over a continuous interval, right? Or a continuous interval of frequency. That's why this is an integral here. Okay? Acha. So here's the point. Okay. यहाँ से e raised by j omega naught n has this Fourier transform, right? And then based on this, based on this, we know that any periodic signal can be written down as a superposition of complex exponentials of this form e raised by j omega naught n, and then I can just apply linearity and find out the Fourier transform of discrete time periodic signals in pretty much a similar way as I did in the continuous time case. Okay? यहाँ पे कोई questions before I move on to the examples?
हाँ सर, ये जब हम एनालिसिस करते हैं तो e की पावर j w जब हम x वापस निकालना पड़ता है, x of n discrete signal original, तो सॉल्व वापस के सेट से मैं समझ नहीं पाया कि कैसे करते हैं कि इनवर्स फूरियर ट्रांसफॉर्म का जो है कैसे करें क्योंकि e की पावर j w1 करता क्या है सर एग्जैक्टली फायदा ये किससे है
So e raised by j omega n is, ये आप e raised by j omega n की बात कर रहे हैं कि ये e raised by j omega n, e raised by j omega n क्या होता है? Is a complex exponential, right?
yes
Right? And we've said in the beginning of the course, these are the fundamental building blocks of all signals, right?
yep
And the reason why I said that at the beginning of the course is because of Fourier analysis. Fourier analysis basically tells you that e raised by j omega n or e raised by j omega t are fundamental building blocks of all discrete time signals and periodic signal and continuous time signals respectively. Okay? All we're doing here is trying to break up discrete time signal, which is x of n, into its those basic components of e raised by j omega n. How do we do it? We do it through this projection. Okay, असल में projection कर रहा है. This is something I sent sometime के basis की तरह भी आप इसको imagine कर सकते हैं. So e raised by j omega n is that basis function. और आप जो है x of e raised by j omega को निकालने के लिए x of n को उसके ऊपर project करते हैं e raised by j omega n पे. Right, so
सर एग्जैक्टली सर ये प्रोजेक्शन मतलब क्या कर मल्टीप्लाई करते हैं या फिर मतलब कि e की पावर j w नॉट एन जैसे वो क्रॉसेस जो
you see you're multiplying by e raised by j omega n, right? You're
Yes.
multiplying x of e raised by j omega with e raised by j omega n, and then you're integrating over omega.
ठीक है
फिर रिजल्ट किसका फंक्शन आएगा?
ओमेगा का
After you've done, no, after you've done the integration, it's not going to be function
n
of
का
omega.
n का
n, and that's what x of n is.
ठीक है
ठीक है? अच्छा, anybody has a problem with this integration? किसी सबसे हो गई है? सबसे हो गई है, right? So it's important for you to so once again, this is fundamentals from the beginning of the semester, and all we're doing is we're using the sampling properties of the delta function. Okay, and the key is that this is over one finite interval, और उस finite interval के अंदर इसकी सिर्फ एक delta function आता है, एक impulse आती है, and that's what I've used, and it doesn't really matter what interval you're at. Okay. Acha, should I go on? Any questions? Okay. So then this is just a simple example. So let's start with this cosine 2 pi by 5n, and I've been asked to determine the Fourier transform for this in the interval minus pi to pi. All I do is I just find out what its Euler expansion is. E raised by j 2 pi by 5n has a Fourier transform, which is a train of impulses, and the one of the impulses is going to be in the frequency at 2 pi by 5, and इसके अलावा just keep in mind that I've only depicted these impulses in the interval between minus pi to plus pi. इससे बाहर वाली there are implicitly all of those impulses there. I've not just drawn them. Okay. इस तरह minus 2 pi by 5n e raised by minus j 2 pi by 5n is going to be impulse at minus 2 pi by 5, and then x of n, because x of n is the sum of these two, तो Fourier domain भी sum आ जाएगा एक impulse 2 pi by 5 पे, एक impulse 0 पे, minus 2 pi by 5 पे. अच्छा, why is the height 2 pi? Why is the height pi?
Sir, 2 से cancel हो जाएगा.
Exactly. So e raised by j 2 pi by 5, and remember there's a 2 pi here. ठीक है? E raised by j 2 pi by 5n के Fourier transform has a 2 pi here, and if I multiply it with a half here, so that half is going to cancel with 2. Good. अच्छा, slightly different example, which is cosine 6 pi by 5n. Right? And then once again, I ask you to find the Fourier transform within the interval minus pi to plus pi. And e raised by j 6 pi by 5n को मैं Fourier transform निकालता हूँ. So it's a train of impulses once again. जो एक impulse है वो 6 pi by 5 पे है, right? But that's outside of the interval pi. And then all I do in order to find the impulse between minus pi and plus pi, I just find out कि इसकी अगली कॉपी किधर होगी, अगली या पिछली कॉपी किधर होगी. पिछली कॉपी minus pi और plus pi के दरम्यान में आएगी, which is just 6 pi by 5 minus 2 pi. which is just minus 4 pi by 5. So this is actually has another copy at minus 4 pi by 5. Similarly, minus 6 pi by 5 n की copy एक minus 6 pi by 5 omega equal minus 6 pi by 5 पे, and then there's another periodic copy of it which has a frequency of this plus 2 pi, and which is at 4 pi by 5. Okay, so in conclusion, from minus pi to plus pi, I have two impulses, one at minus 4 pi by 5 and another one at plus 4 by 5. Achha. And so this is the Fourier transform. Okay. Now, is Fourier transform. So one of the things I said at the end of the module is that, let's say if I had another signal which had the frequency of 4 pi by 5, cosine 4 pi by 5 n, I would have found that the Fourier transform for this would have exactly been the same as the Fourier transform of 6 pi by 5, cosine 6 pi by 5 n, right? So since there's a one-on-one correspondence between the time domain signal and the Fourier domain signal, then this would have meant that cosine 4 pi by 5 n must be equal to cosine 6 pi by 5 n, right? Is that true? Because if it's not true, then what we've done up above, there's something wrong with that. So is cosine 4 pi by 5 n equals cosine 6 pi by 5 n? The Hassan? Okay, जी सही.
यस सर इक्वल होंगे क्योंकि अगर माइनस 2 पाई से अगर हम सब्ट्रैक्ट करते हैं तो माइनस 4 पाई बाय 5 आएगा और कॉस इवन फंक्शन है तो माइनस
Excellent. So just make it a point कि जी 2 pi से सब्ट्रैक्ट करना है तो you're actually saying that cosine 6 pi by 5 n is cosine 6 pi by 5 n minus 2 pi. I know that's true, right? लेकिन अच्छा sorry. Hold on. Okay, so cosine 6 pi by 5 n equals cosine 6 pi by 5 n minus 2 pi. Said, is this what you were saying?
Yes, sir.
लेकिन इससे आंसर नहीं आएगा. You won't get the desired result here. Because, I mean, how do you show that this is cosine minus 6 pi by 5 n? So even though this is true, I mean, you would have to use the periodicity and the frequency. So asil mein, even if there's any integer multiply with 2 pi, even then that's true because of the periodicity of cosine. Okay? And then I can say this is cosine 6 pi by 5 minus 2 pi times n, right? And this is cosine minus 4 pi by 5 n. And since cosine is an even function, as you just said, therefore cosine minus 4 pi by 5 n is cosine plus 4 pi by 5 n. Okay, so this is actually true. Okay, Jamshed? Okay, so let me. Acha. And then there's the Fourier transform of this train of impulses. Isme koi question? So once again, and the reason why I did this example particularly was because here we cannot rely on that Euler's expansion. Okay? We'd have to go and find out the Fourier series expansion first, and then use linearity, and then the basic result that we just derived, which is this result here. So सबसे पहले जो train of impulses हैं, x of n equals summation k equals minus infinity. So it's a train of impulse in the time domain. I just find out what the Fourier series representation for this is in discrete time, and this is something we've done. I'm not going to do it here again. So ak this turns out to be equal to 1 by n, right? All of the Fourier series coefficients are 1 by n. Okay, and then because of which I can conclude that x of n is equal to 1 by n, and then summation k equals 0 to capital N minus 1 e raised by j k 2 pi by n capital N times small m. Now, what is the Fourier transform for this? This is something we've done just now in between 0 and 2 pi is going to be an impulse, because 2 pi by n is smaller than 2 pi. Okay? So for k equals 0, this is an impulse that you're going to get, right? So this is the Fourier transform within 0 and 2 pi of 1 upon e raised by j0. This is the Fourier transform of the term 1 upon n e raised by j times 1 times 2 pi by n. So k equals 1 here. This is the Dtft of the term corresponding to k equals 2 and so on and so forth. K equals capital N minus 1 वाली term जो है यहाँ पे आखिर में आएगी, ठीक है? So this is one copy, right? And then I know for a fact that this transform needs to be periodic in the frequency with a period of 2 pi. So मैंने क्या करना है, ये पूरा का पूरा उठाना है, right? पूरे की पूरी window उठानी है ये वाली और इसको periodically extend करना शुरू कर देना है, right? And since all of these are constants, is of the same height of 2 pi by n, right? All of them have the same height of 2 pi by n. So it turns out that minus infinity से plus infinity पे you're actually going to get a constant train of impulses, right? जिसमें height सबकी 2 pi by n होगी, and they will be separated by in the frequency with an interval of 2 pi by n. So this is the final result that you get, right? So this is the final result that you get. And similar to the continuous time case, once again, the Fourier transform of a train of impulses in the discrete time is also a train of impulses. Okay? Any questions here?
सर हम इस मेथड को जनरलाइज कर सकते हैं, मतलब फोरियर सीरीज कोएफिशिएंट्स किसी को भी पता हो तो हम यही वाला यूज करें.
Exactly. Excellent. So any Fourier series coefficients that you know of, so now you can कोई भी मैं आपको periodic signal दे दूं discrete time में, और and I ask you to determine the Fourier transform of it. So all you need to do is you need to determine the Fourier series coefficients is of a naught to a n minus 1, ठीक है? उसके corresponding impulses आ जाएंगी Fourier transform की 0 to 2 pi के दरमियान में, and then just periodically extend itself.
सही है.
ठीक है सही? So this can be generalized. Excellent. Okay, very nice. Any other questions from this before I go on?
सर ये बात दोबारा
कौन सी?
मैं कह रही थी, आप ये रिपीट कर सकते हैं?
जो जनरलाइजेशन है?
यस यस यस.
So जनरलाइजेशन है कि ये है कि let x of n be periodic, right, with period n. So the first thing I know that it has a discrete time Fourier series representation, right? So it has a Fourier series representation, right? And that Fourier series representation just says that x of n equals k equals 0 to n minus 1 a sub k e raised to power j k 2 pi by capital N times n. ठीक है तो बा? Right? तो इसका Fourier transform अगर मैंने निकालना है, right? x of e raised to power j omega. So the x of e raised to power j omega in the interval 0 to 2 pi, वो कैसा दिखेगा? So at 0, you can have an impulse which is going to have a height of what? Is going to have a height of a naught times 2 pi. और यहाँ पे frequency क्या होगी? This is 2 pi by n पे इस impulse की क्या height होगी? This is going to have a1 times 2 pi. Right? At 4 pi by n, this is going to have a height of a2 times 2 pi, and so on and so forth. All the way up to here. यहाँ पे आखिरी impulse कहाँ पे आएगी? This is going to be capital N minus 1 times 2 pi by n, and the height here is going to be a capital N minus 1 times 2 pi. right? So this is a generalization, right? And how do I come about this? From all of that analysis that I did, right? So तो बात समझ आई?
Yes, sir.
तो आपने सिर्फ इसका एक टर्म इसके अंदर लेनी है, right? And you find the Fourier transform of that term, and the Fourier transform of that term is going to be an impulse, right?
ठीक है
So
सर.
a k e raised by j k 2 pi by n times n इसका Fourier transform जो है, this is a k times 2 pi times delta omega minus 2 pi k upon n. There's a caveat here, and that this is the Fourier transform within the interval 0 to omega to 2 pi. Okay. So, and then I just have a linearity here. So there's a summation here. So this summation here, superposition का. Okay.
Yes,
Clear
sir. Yes, sir. Thank you.
All right. Acha. So these are some exercises. So let me. ये किसी ने किया ही नहीं की? Okay, good, Said. Anybody else have? Right, so it's important for you to try them. हो गई, Said, were you able to do all of those?
क्वेश्चन 2 नहीं समझ आ रहा था.
Okay. तंजील, ये क्वेश्चन 2 किया आपने?
नहीं सर ने क्वेश्चन 2 नहीं किया.
Okay, so this is similar to one of the questions you answered in the last session I had.
Yes, sir.
So question 2 जो है, I'm just gonna give you a hint here. अच्छा, किससे हुआ है? सैफ, आपसे हुआ है question 2?
नहीं सर, क्वेश्चन 2 नहीं हुआ.
हुआ नहीं है, ट्राई नहीं किया अभी?
सर ट्राई किया था मगर हो नहीं रहा था.
Okay, so you just look at this, ठीक है? और you go back, जो अभी नवीद ने at the very beginning he said something about duality, right? And चले उस duality को चले भूल भी जाएं. You see here that this function is actually is a signal, but the independent variable of this signal is omega. But this signal is periodic, isn't it? मैं सिर्फ ये वाला अगर सिग्नल देख रहा हूँ, ये वाला सिग्नल देख रहा हूँ, ये पीरियोडिक है या नहीं है?
यस सर, पीरियोडिक है.
Periodic, right? So periodic in the frequency domain, and it's actually a train of impulses in the frequency domain, right? Now I know that any periodic signal has a Fourier series decomposition, right? Or most of them, and this satisfies that Dirichlet conditions. ठीक है? तो इसकी Fourier series representation होनी चाहिए, except with the caveat that the independent variable here is not time anymore, but rather the independent variable is omega. ठीक है? अगर independent variable omega है, तो इसका doesn't really matter. I can still find the Fourier series representation of it. Okay, and you go ahead and try to find the Fourier series representation of this periodic signal with omega as the independent variable, and you will find that this is the Fourier series representation. And you see, this is similar to Fourier series representation anyway. Right? This is multiplication of summation of complex exponentials in the frequency domain, with omega as the independent variable. Okay, that's one way to think about it. The other way is कि और ये अगर ना होता तो फिर आपका जो पुराना रिजल्ट था वो खराब था, right? You see here, मैंने यहाँ पे डिराइव ये किया है कि x of n, which is, अच्छा वो स्क्रीन वापस नहीं जा रही. Okay, so I'm having technical glitches here. Give me a minute. So for some reason I can't. Sorry guys, I had issues. So let me start again. Okay. आवाज आ रही मेरी?
Yes, sir, आ रही है।
Okay. So where was I? हाँ, मैं ये कह रहा था कि just like in the one of the previous sessions as well. So if I take the Fourier transform of this thing here, okay, I know that this is the Fourier transform. This is a train of impulses, right? But if I apply the linearity property, the linearity and the time shifting property, as we will see later, आप इसके ऊपर लगाएंगे तो आप will find out that this must be a summation of exponentials, right? But since I cannot have two different results, so that summation of exponentials must be equal to this thing here as well. And that's another way to think about this. कि वो that Fourier series analysis जो आप कर रहे हैं frequency domain में, वो that's another implication of or another way of to confirm this application of linearity and exponential. Just like पिछली क्लास में किसी ने क्वेश्चन एग्जैक्टली यही पूछा था कंटिन्यूस टाइम केस के लिए, ठीक है? So I'll not say a lot more about this. I'll let you think about this on your own. एक्सरसाइजेस के अलावा जो एक जो इम्पोर्टेंट पॉइंट है, ये क्वेश्चन 3 वाला है, right? Did somebody think about this? जी सर.
So the complex number signifies that the frequencies will repeat themselves after 2 pi because complex numbers also are circular. Okay, good.
Right, so that's one of the primary reasons why we use this notation x of e raised by j omega, and that is kg e raised by j omega. If you recall, it's e raised by j theta is an equation of a circle. As theta goes from 0 to 2 pi, I mean that you're representing you're moving on a circle, and then when after 2 pi you're just back and circularly वापस उन्हीं frequency पे आ जाते हैं, right? So this just represents that omega has a wraparound effect, or the frequency domain may there's a wraparound effect in the frequencies. There's a periodicity in the frequency with the period of being equal to 2 pi. That's one of the reasons why we use this notation instead of this notation, which is still a valid notation. जो आप I think जो उसकी book है ओपनहाइम की है, Trocki's की जो book है of for signals and DSP, he uses x of omega, does not use x of e raised by j omega. Okay. इसका एक और रिलेशनशिप z ट्रांसफॉर्म के साथ भी है, वो since we're not doing z transform, but maybe that's a reading assignment for you. यही क्वेश्चन आपको एक और कंटीन्यूअस टाइम फोरियर ट्रांसफॉर्म में पूछना चाहिए था वैसे, कि कंटीन्यूअस टाइम फोरियर ट्रांसफॉर्म में maybe I mean we use this notation x of j omega, right? Why x of j omega? I mean, why was this j here? It's not actually a function of j, right? जी साहब, ये किस लिए था?
So शायद इसलिए क्योंकि वो complex frequencies भी आ जाती हैं.
Yes, that's true. So this has to do with Laplace as well. कि Laplace में Fourier is just the Laplace evaluated on the imaginary plane, or imaginary
Yes,
axis.
sir.
Okay? So this just represents that fact that the frequencies are some complex imaginary axis पे evaluate हो रही है. ठीक है? So थोड़ा सा relationship Laplace के साथ है. Since you have studied Laplace already, so I just wanted to bring it up. So Jamshed, the other book is Prokis की book है, right? For DSP, digital signal processing. Okay, acha. And then finally, properties. Properties are very, very similar, so I'm just going to quickly go over them. Periodicity, we've done this. Linearity, very, very clear. Time shifting n minus n naught in the time domain is multiplication with an exponential in the frequency domain, just like in the continuous time case. Multiplication with the exponential in the time domain is shifting in the frequency domain. So you see there's a duality here as well. And because of this one of the implication is that any signal that you take, you multiply that with minus 1 raised to power n, that's equivalent to shifting the signal in the frequency domain by a frequency of pi. Okay, so if this was x of e raised to power j omega, so the Fourier transform of minus 1 raised to power x of minus 1 raised to power n times x of n is just simply going to be this Fourier transform shifted by pi. So the अगर low frequency signal था, minus 1 raised to power n से multiply करने से वो low frequency signal थक करके high frequency पे चला जाता है, right? That's what the impact of multiplication with a minus 1 raised to power n is. And that makes intuitive sense because minus 1 raised to power n, remember, is a very, very fast signal and actually the highest oscillation that you could have in the discrete time. So it's like there's here and then all of a sudden it's in the negative and then all of a sudden it's positive. It's all of a sudden it's negative. Okay, you multiply with the signal, the effect is frequency shifting. All right. Now, my question to you is, अगर मैं ये वाला signal लूँ, some signal which had a peak at pi, and then I multiply, so I take a signal which was already high pass, right? It already had high frequency components. I multiply that with minus 1 raised to power n. What happens then? जी ईमान क्या होगा फिर?
सर आई थिंक वो वापस से वो बन जाएगा पहले वाला.
क्यों? Good, that's the right answer.
सर बिकॉज अगेन फ्रीक्वेंसी शिफ्टिंग होगी और वो फिर 2 पाई पे शिफ्ट हो जाएगा और पीछे वाला सैंपल 0 पे शिफ्ट हो जाएगा.
Excellent, excellent. So if I just multiply this again with minus 1 raised to power n, this is further shifted by pi, ये copy 2 pi पे चली जाएगी. But since this is periodicity, to 2 pi वाली copy 0 पे भी होनी चाहिए, right? So the same copy actually appears at 0 as well. Another one of the ways you can think about this, if you multiply this signal twice with minus 1 raised to power n, what do you get? You get the same signal back. Okay, minus 1 raised to power n times minus 1 raised to power n is just 1. Right? So minus 1 raised to power n times minus 1 raised to power n क्या होता है? So this is always 1. Very basic stuff. Right? So minus 1 raised to power n times minus 1 raised to power n is always 1. ठीक है? अच्छा. Time reversal is straightforward. Conjugation is straightforward as well. और time reversal और conjugation की वजह से सारी की सारी जो symmetric property, conjugate symmetric properties जो हमने continuous time case में, Fourier transform में, Fourier series में की थी इससे पहले, all of them apply here as well. So that's why we're not going to go into those details. This does not mean that we're not that's not included in the coverage. Okay, but since this is very, very similar, the conjugation symmetry properties are very similar, are exactly the same actually as what we've done earlier. So we're not going to go into them right here. Okay, multiplication property. If I multiply two time domain signals in the Fourier domain, they are convolved, just like in the continuous time case, with the explicit difference being what? That the convolution is periodic. The convolution is not from minus infinity to plus infinity in the frequency domain, but rather over a finite interval of length 2 pi. Okay, so this is something you can prove. It may be in the textbook as well. Yeah, maybe end of chapter problem as schema color. And then there's Parsifal's relationship is if I compute the energy in the time domain, I can also compute the energy of the time domain signal from the Fourier domain. How? I just take the Fourier transform over any interval of n 2 pi. I take the absolute squared of it and find the area under the curve. That is, and scale by 2 pi. That is going to give me the energy in the time domain signal. And that's why this term here is called the energy spectrum density, right? So actually, यहाँ पे 1.25 भी चले. Strictly speaking, ये भी होना चाहिए. So this term is called the energy spectrum density. Okay. So at any omega, so this is x of e raised by j omega. Any omega, यहाँ पे omega किसी omega पे मैं value निकालता हूँ. What does this represent? This represents the contribution of the exponential of frequency e raised by j omega n in the time domain signal. And moreover, it also represents, if I take the absolute squared of this quantity, right, and scale by 2 pi, this represents कि मेरे signal में इस frequency की वजह से energy कितनी है. I mean, that's what the information this value is telling me. That's another one of the information this value is telling me. Okay? And the reason why it's called the energy spectrum density is because if I integrate this entire curve and I take the absolute square of it and integrate over the frequency, then I get the energy. Okay? इसके unit इसका मतलब क्या होना चाहिए? Energy per frequency क्या होनी चाहिए? Right? So इसके अगर unit energy per frequency के, that's why it's called the energy spectrum density. Okay? Any questions here? Okay. ये कर ली किसी ने? Exercises. जी सर, are you done with both of them? होगी?
Yes sir, I tried both of them sir, but पहले वाले का आंसर ठीक नहीं आ रहा था. तो जो आपने करवाई थी ना बाद में, उसके अंदर n+1 आ रहा था, मेरा n-1 आ रहा है.
अच्छा चलें, so at the end of this session we can do this exercise here. ठीक है? Okay. And finally, the convolution property, right? Convolution property is similar to the continuous time case. Okay, if I have two time domain signals, x of n and h of n, which have Fourier transform x of e raised by j omega, h of e raised by j omega, if I convolve those two signals in time domain, in the frequency domain, their Fourier transforms are multiplied together. Okay, that's a theme that we've been coming across over and over again. And just like in the continuous time Fourier transform case, the same ideas extend to the discrete time case as well. What that means is that x of n is a discrete time signal जो कि मैं एक LTI system में डालता हूँ, और LTI system का impulse response h of n होता है, और output मेरे पास y of n आती है. The Fourier transform of y of n is going to be equal to the Fourier transform of the input times the Fourier transform of the impulse response of the LTI system. And the Fourier transform of the impulse response of the LTI system is called the frequency response of LTI system, right? And it is because of this multiplication that we think of LTI systems as filters, as frequency selective filters, because this helps, this h of e raised by j omega is going to help shape what the output is going to look like as a function of the input. In other words, अगर input के कुछ frequency components आपने block करने और कुछ frequency components आपने amplify करने, right? So for example, in this case here, you want to pass this frequency component of the input as it is to the output and block these pink ones out. So the way you're going to design h of e raised by j omega is to have the h of e raised by j omega look like this ideal square pulse, which is equal to 1 from minus omega to plus, from minus w to plus w, and is 0 all at all other places. Okay, so this is an ideal low pass filter, okay, is equal to 1 from minus w to plus w and is 0 at all other places. Okay, and if I do this multiplication, therefore, of the blue signal with the Fourier transform of the original signal x of h by j, the output I'm going to get is just this copy left out and this one cancelled out. Okay, so ye pass ho gaya, so yellow one passes and the pink one is just blocked out, and that's why it's LTI systems are also known as filters. Okay, because they filter something out. Okay, and this is an ideal low pass filter जिसका अगर मैं ट्रांसफॉर्म इनवर्स ट्रांसफॉर्म निकालूं, what do I get? Inverse transform. Inverse transform, I just plug in h of e raised by j omega inside the inverse Fourier transform relationship, or karte karte, I mean, so this is straightforward going from here to here. This is sine omega n by pi n. This is the Sinc pulse. Okay, and this is the Sinc pulse which has an envelope which looks like this, और बाकी हर जगह पे ये यहाँ पे ones होंगे, sorry samples होंगे उसके. ठीक है, अच्छा, Jamshed says is this a modulation property? This is not the modulation property, right? This is very different from the modulation property. Jamshed, what was the modulation property? You can think of this as a dual of the modulation. Yes. So modulation में we were if we multiply two signals in the time domain, what happens in the frequency domain is convolution. That's a modulation property or the multiplication property. This is the convolution property. We're not multiplying two time domain signals, rather we're convolving two time domain signals. इसकी वजह से frequency domain में multiplication हो जाती है. ठीक है? Okay, जमशेद? अच्छा, यहाँ पे and then the digital signal processing वाली I gave you this application example. अगर वहाँ उससे कोई questions नहीं है तो I'm going to skip that and move on. You can say this is convolution property or filtration property. I'm not sure if anybody uses that term. I use this. I would use convolution property. Okay? If you want to come up with your own term, that's fine. No problem. Okay, Jamshed? All right. Any questions here before I answer Sav's question that he said?
सर ये लो पास जो हमने फिल्टर रिज्यूम किया था अभी, ये फोरियर डोमेन में जो हमने लो पास फिल्टर रिज्यूम किया था, इसका इम्पल्स रिस्पांस एक रेक्टेंगल था, लेकिन ये कॉन्टिन्यूअस है. अगर हम इसको इन्वर्स करते हैं तो हमारे पास जो सिंक आता है वो डिस्क्रीट टाइम है. तो सर इस तरह तो इसकी ड्युअलिटी होल्डिंग करनी चाहिए.
अच्छा, इसे डायरेक्ट इस तरह की ड्युअलिटी नहीं होती इसलिए.
सही है सर, तो ड्यूअल नहीं है ना, जैसे कंटीन्यूअस में
कंटीन्यूअस टाइम में जो ड्युअलिटी थी वो दैट वाज ड्युअलिटी इन द फ्रीक्वेंसी एंड टाइम डोमेन. यहाँ पे जो ड्युअलिटी शुरू में मेंशन की है फॉर एग्जांपल नवीद ने भी, that duality was a slightly different duality. That duality was of the discrete time Fourier transform with continuous time Fourier series के साथ duality थी.
अच्छा अच्छा, सही है.
ठीक है, so that was, but that's a good question. Okay. Any other question? So रात को सैफ ने ये पूछा था कि I know if I have an ideal low pass filter h of e raised by j omega, so let's say this is x of e raised by j omega, which is minus omega w से plus w तक उसकी height 1 है, and if I take the inverse Fourier transform for this in the time domain, I get x of n equals sine wn divided by pi n, right? And of course, w here was between 0 and pi. Okay, so let's call it here, right? So what that means is if I take the Fourier transform of this thing here, right, where w is in between 0 and pi, I am going to get this ideal low pass filter. Okay, but for this, w has to be between 0 and pi. W has to be between 0 to 2 pi, 0 to between 0 and pi for this transform relationship to hold, right? Second question ये था कि what if I give you another signal, which is x of n, which is a sinc pulse, which is sine wn divided by pi n, and let's say ये कहते हैं pi is less than w is less than 2 pi. What is x of e raised by j omega? So what do you think it would look like? जी सैफ आपको आंसर मिला या नहीं मिला?
सर सोचा नहीं है इतना इसके ऊपर सर, बट ये कि if w is between pi and 2 pi, you'd get the same frequency response.
देखिए इसमें थोड़ा सा मसला है क्योंकि अगर आप if pi w is between pi and 2 pi and then what you're saying is कि ये चीज असल में you're saying is कि ये चीज ये वाली जो लेंथ एंड है it goes all the way pi से आगे चली जाती है, तो there are implications of periodicity जो कि मसला कर सकती है, because if copies are summing on top of each other तो एक कॉपी तो उधर से भी आनी है, तो फिर तो ये स्क्वायर वेव नहीं रहेगी, वो तो ओवरलैप्स आना शुरू हो जाएंगे and so on and so forth.
हाँ yes sir जी.
Okay, so that's why it's slightly problematic. Moreover, you know कि यार frequency जो ideal low pass filter है, right, और the unique frequencies are always between minus pi and pi. ठीक है, so if you're just considering frequency between minus pi and plus pi, a frequency of greater than pi doesn't make sense. I mean, that wraps around anyway. ठीक है, so my approach to this would be to try to find an equivalent for this because of the periodicity of the sine function, an equivalent for this which ensures कि यहाँ पे जो आपके पास जो कोई frequency आ जाए वो दोबारा से minus pi और plus pi के दरमियान में आ जाए, right? So right now w is between w is in between pi and 2 pi. So here's where w is. मैं इसकी and I know कि sinusoid is periodic, right? With in the frequency as well. तो w की frequency का एक counterpart जो है w minus 2 pi भी होगा, और w minus 2 pi हमेशा इधर लिखिएगा, in between minus pi and 0, right? So the way I'd go about this is the following. So I'd say this is sine omega n minus 2 pi n divided by pi n, and this is just sine omega or w minus 2 pi times n divided by pi n, right? So if pi is less than w is less than 2 pi, w minus 2 pi कहाँ से कहाँ होगा? So this is between 0 and this is minus pi, right? So it's actually w minus 2 pi is negative, right? So therefore, this is minus sine 2 pi minus w times n divided by pi n, right? And so therefore 2 pi minus w is less than pi is less than 0. Now you have the answer. Okay, now you're looking at a Sinc pulse. You're looking at a Sinc pulse. You're looking at a Sinc pulse. जिसकी frequency ये w एक ऐसा है, right, which is between 0 and pi. So इसका Fourier transform क्या दिखेगा? अब Seth, can you tell me what the Fourier transform?
The Fourier transform will reflect along the x-axis. So you'll get an inverted Sinc function.
Inverted rectangular.
Oh, yes.
ठीक है, और इसके कट ऑफ क्या होंगे?
2 pi minus omega minus w and minus 2 pi minus w.
Excellent. This is 2 pi minus w, and this is w minus 2 pi. So this is still a low pass filter, except that it's an inverted low pass filter. यानी उस तरफ negative उस signal की polarity reverse कर देगा. ठीक है? So, but that was this was an excellent question. Okay. Right. Any questions here?
Sir,
Yeah.
sir, how did you calculate the cutoff frequency?
How do I come up with the cutoff frequency? ये 2 pi by minus w क्यों होगा?
Yes, sir.
So that's based on this known relationship.
Okay, sir. ठीक है.
ये जो चीज़ है ना, ये known है मुझे.
ठीक है, sir.
लेकिन इसके लिए ज़रूरी क्या है? इसके लिए ज़रूरी ये है कि w here has to be between 0 and pi. Maths ऐसी होती है कि you know some things, and then if you don't know something, you try to convert that something you don't know into something you know. ताकि आप जो something you know, just apply it directly. And that's what I've exactly done. I know this already, right? And then all of a sudden what I've been given looks similar to what I know, but not exactly. Because what I know has w between 0 and pi, but this w is not between 0 and pi, but rather into between pi and 2 pi. So all I've tried to do next is to try to manipulate it somehow so that I convert it into some form which I know already, right? And all of these equations evaluate karte, this is where I get. And now for a fact, I know that 2 pi minus w is in between 0 and pi. And this is something I know already. Okay, so I've converted this to this form, jiska knowledge hai mere paas, right? And then, yeah, so I know that the Fourier transform for this is a rectangular pulse, and this, because of the minus sign, is inverted. Okay, Tuma?
Yes, sir.
Okay. Acha, then finally, this was an example that I did at the end. So one of the other benefits of the convolution property is that you can use it to compute convolution, right? The x of n convolved with h of n agar aapne karna hai, so one of the ways you could do it is you just find the Dtft of x, you find the Dtft of h, you multiply the Dtfts of x and h, right? And then find the inverse Fourier transform of the product, and that's going to give you the convolution. Okay, is that clear? That's what we did in the continuous time case as well. This which is exactly what we do here as well. Okay, as one of the shortcuts. Right? For this particular example, when alpha equals not equal to beta, x of e raised by j omega is something we know from the first example that Naveed covered. This is 1 minus beta e raised by minus j omega. This is 1 minus alpha e raised by minus j omega is a product here, and then you just apply a partial fraction expansion, right? So there's a constant capital here, there's a constant capital B here. You can find those constants, which turn out to be these. And as a result, this is your final answer. And you can and you should try to verify if you convolve x and h, what result do you get? You should be able to verify this is exactly the result that you're going to get. Okay. A corner case here, of course, is when alpha equals beta, because when alpha equals beta, so alpha equals beta, ये भी 0 हो जाता है और ये भी 0 हो जाता है. So you get a 0 by 0. So you'd have to either apply L'Hopital's rule, which you can actually do, but that's slightly more involved in the sense कि आपने किस चीज़ में differentiate करना है, that's something you'd have to figure out. One of the other ways is you just go in here and just plug in alpha equals beta, because when alpha equals beta, this partial fraction expansion is not valid. So this is when alpha equals beta. So screen मेरी फिर से hang हो गई है. So when alpha equals beta, this is y of e raised by j omega और ये known result है, ठीक है, जो कि एक exercise है, right? Any questions here? Okay, so we have 4 minutes. I can do one exercise. कौन सी वाली exercise? वो differentiation वाली कर लें. Okay. Okay, Jamshed has a question. How did we get the discrete time expression at the end? कौन सा वाला? ये वाला?
Yes, sir.
Jamshed, this is a known result, which is an exercise, which I'm going to do now. So this is exercise. So the x of e raised by j omega, if it's this form, 1 upon 1 minus alpha e raised by j omega whole squared, what is the inverse Fourier transform for this? That's something you need to evaluate. Okay. So let me do this here. So I use the differentiation and the frequency property, right? So we use the what is that differentiation in the frequency property? That says that if the Fourier transform of n times x of n is what is equal to j times d by d omega of x of e raised by j omega. So this is something I'm going to use, right? Why do I use this? ये बताइए जरा मुझे कि because I am familiar with something which is alpha raised to power n u of n का Fourier transform क्या होता है जमशेद?
Sir, I don't know.
This is 1 upon 1 minus alpha e raised by minus j omega. Okay, and I see that the required this thing here, right? In order for me to get this thing in pink from this thing here, if I differentiate with respect to omega, नीचे square आ जाएगा. Okay, with some other terms as well, which I'm going to be able to manipulate later. Okay, so that's why I use the differentiation property in the frequency, because if I differentiate with respect to omega, I'm going to get something which is a squared in the denominator. So let me just apply that. So this is n times alpha raised to power n u of n. We'll have a Fourier transform of what? The Fourier transform for this is going to be differentiate of this with respect to अच्छा, इसको differentiate करें जी जरा. So I'll wait for 2 minutes and I'll let you differentiate this on your own. I mean, based on my experience, majority of the students stumble here. जी सर, आपने कर लिया हुआ है, I believe differentiate, right?
सर वो मैं कह रहा हूँ सर d/dw के लेफ्ट साइड पे j भी होगा।
j होता, sorry. Thank you.
सर आंसर भी बता दूं?
नहीं, आंसर जरा बाकी लोग भी कर लें, मुझे नहीं पता कर रहे हैं नहीं कर रहे, I cannot watch them.
सही है सर।
So let's give them a minute and then I'll ask you. Okay, किसने कर लिया differentiate? जमशेद हो गया differentiate? Okay, so there's no जमशेद 1 plus alpha तो नहीं आएगा, लेकिन something similar. पीछे square आएगा, that's right. Who else? Tuba?
Yes sir. सर मेरा आंसर आ रहा है प्लस अल्फा ई जे डिवाइड बाय 1 माइनस अल्फा ई जे ओमेगा होल स्क्वायर।
Okay, good. That's right. So the way I'm going to differentiate this is ye aya, right? So this is j is which I had in the outside. This is 1 minus alpha e raised to 1 minus j omega whole squared. Okay, and there is a minus sign because this was raised to power minus, because this was minus 1. Okay, वो minus 1 उधर आ गया नीचे, right? Okay, good. So उसके बाद क्या हुआ? And then I differentiate alpha e raised to power minus j omega with respect to omega. इस minus की वजह से ये minus ये plus हो जाएगा, and then this is alpha times e raised to power minus j omega, and then differentiate this thing here with respect to omega as well. So this is going to be minus j on the outside. ठीक है? Or and then I can j times j is minus 1, and there's a minus 1 there already, so this is alpha e raised to power minus j omega times 1 minus alpha e raised to power minus j omega whole square. ठीक है? तो भाई यही आप कह रही थी?
Yes sir.
Right. So what we have is alpha n times alpha raised to power n u of n has a Fourier transform, which is alpha e raised to power minus j omega upon 1 minus alpha e raised to power minus j omega whole square. लेकिन this is not what I want to write. मुझे ये चीज गायब करनी है, ये चीज गायब करनी है, तो ये गायब कैसे करूं?
सर आप डिवाइड कर देंगे इससे न्यूमरेटर में और डिनोमिनेटर।
I can divide by alpha, चले ठीक है. So I can divide by alpha. So if it's 1 by alpha here, I can have 1 by alpha here. So which would mean कि n times alpha raised to power n minus 1 times u of n. This has a Fourier transform of e raised to power minus j omega of 1 minus alpha e raised to power minus j omega. ठीक है? e raised to power minus j omega को कैसे निकालूं?
So shifted impulse हो जाएगी, shifted step function.
Shifted function, good, right? So this means कि n plus 1 alpha raised to power n u of n plus 1. If I shift the time domain signal by plus 1, what happens in the Fourier domain? Fourier domain में this would be e raised to power plus j omega times the Fourier transform of the original signal that I had here. So this is e raised to power minus j omega times 1 minus alpha e raised to power minus j omega whole squared. Right? So this means n plus 1 alpha raised to power n u of n plus 1 ka Fourier transform. That is what I was actually looking for. Okay? And I can further say that ये जो चीज़ है ना, this is actually equal to n plus 1 alpha raised to power n times u of n. ये कैसे आया? तुबा? चले तुबा नहीं उबैद?
He said,
How do I get from here to here? सही ने हाथ खड़ा किया हुआ ये सही
Because at n is equal to -1, the signal is 0. So
Good.
we can say
Excellent.
that it's not defined.
Excellent, right? So you see कि जी n equals -1, ये n equals -1 पे start होता है, right? But n equals -1, if I plug in n equals -1, the signal is 0. So the signal is 0 at actually n equals -1. So therefore, it doesn't make a difference if I have a u of n here. Okay? So this is the result, which is exactly the result, Jamshed, that I used in the last example. Okay? So this is a known Fourier transform pair, by the way. So this is a known Fourier transform pair. So it's 1 upon 1 minus alpha e raised to minus j omega whole squared. Isme, of course, one of the things that's important is the absolute value of alpha is less than 1. Otherwise, this does not hold true. If absolute value of alpha is greater than 1, फिर क्या होता है? फिर क्या होगा? क्यों तंजील?
सर डाइवर्स करना स्टार्ट हो जाएगा.
Exactly, and the Fourier transform does not converge them.
Yes.
Does not exist. Okay, good. Any questions here before I end?
सर तो आप फाइनल एग्जाम किस देंगे सर? फाइनल
एग्जाम मंडे को है
तो किस तरह का होगा सर? कि आप क्या क्वेश्चन
यस
हमें पिक्चर्स देके पीडीएफ बना के आपको भेजना पड़ेगा या फिर
आपने क्विज किया था?
क्विज किया था वैसे ही?
हाँ, so you'd solve it on a piece of paper, on pieces of paper, okay, and then take a picture and upload.
Okay.
Okay. Jamshed, I'm going to come back to you. Saif has raised his hand. Yes, Saif.
सर एक्सरसाइज 37E का क्वेश्चन 1 है सर, आप उसका सिर्फ फाइनल आंसर अपलोड कर देंगे ताकि पता लग जाए जो वर्किंग किया वो ठीक किया?
सॉरी, एंड ऑफ चैप्टर?
नहीं सर, जो आपने एक्सरसाइजेस अपलोड की थी एलएमएस पे.
अच्छा 37E
क्वेश्चन 1.
ओके, क्वेश्चन 1 का
आप
ए
सिर्फ फाइनल आंसर अपलोड कर दें.
हाँ, सो मैं जिसका ये सिर्फ पाई पे आएंगी सैफ
जी,
मैं आपको क्वेश्चन आंसर बता रहा हूँ. पाई पे इंपल्सेस आएंगी.
ए पार्ट की हाँ जी.
So pi भी आएंगी. सिर्फ there's going to be an impulse at pi.
जी.
ठीक है, and then 3 pi and then 5 pi और periodically extend करेंगे.
ठीक है सर.
ठीक है, और height उसकी जो है 2 pi होगी.
सही है सर.
ठीक है. अच्छा, ये कर दिया?
जी सर, सी पार्ट भी किया.
और डी पार्ट?
डी पार्ट भी किया.
सी और डी में क्या फर्क है?
सर सी और डी में फर्क है कि सर डी पार्ट में ये तो था ना कि इफ n वाज इवन तो फिर हमारी इम्पल्सेस 2 पाई बाय n ऊपर की तरफ था, और अगर d वाज ऑड तो फिर सब वो नीचे की तरफ आ रही थी.
You see, okay, so if n was even, so this actually reduces to the previous example.
जी जी
If capital N was odd, तो ये C बन जाता है.
जी
बारे में सोचिएगा थोड़ा सा.
ठीक है सर.
ठीक है. अच्छा. Jamshed, if you have this function in the time domain, you cannot have this function in the time domain because that function is continuous time. Discrete time नहीं है वो. ठीक है. Okay. So once again, we have our quiz tomorrow at 3 p.m. and we require to submit your solution by 4:15 p.m. Okay. So the quiz by itself, we're going to try to plan it. कि अगर आप continuous उसको कर रहे हो तो 20 minutes में you should be able to attempt it. 20 to 30 minutes, and then the extra time is there for any interruptions that you may experience or any internet connectivity issues or anything. Okay. Any questions about the quiz? The quiz will be from the content that we've done today, right? Or actually was uploaded last week. So let me put it like that.